Object detection is one of the fundamental problems in computer vision and has been widely applied to robotics and autonomous driving. Its target is to classify and localize all objects of interest from the sensor input. For example, in the RGB camera image shown below, 3 objects are detected. They are classified as fan, cyclist, and pedestrian, and localized with bounding boxes. In recent years, deep learning has advanced many computer vision problems and has become the de facto methodology in object detection. On the right image, you can see the evolution of top methods on the standard VOC object detection benchmark over the past decade. All top object detectors are based on deep learning since this technology was introduced in 2014, and the detection accuracy is improving consistently. However, by the time when I started my PhD in 2017, all these deep object detectors were deterministic, without any uncertainty estimates in bounding boxes. As a result, those detectors only predict what they see, but not how uncertain they're about it. For autonomous driving, those deterministic object detectors are not enough. We need probabilistic detectors. Because when deploying autonomous cars in the wild, we may face a lot of challenges, such as adverse weather, night drive, or scenarios with many new objects. In those situations, object detectors may make predictions with errors and failures. Uncertainties that reflect those perception errors or sensor noises will provide very valuable information to introspect or self-check the perception performance and help a car react accordingly. For example, when a front car is detected with high uncertainty, the autonomous driving car can decide to slow down in order to avoid potential collision due to misclassification. Therefore, capturing reliable uncertainty is crucial when considering safety for autonomous driving. In this context, the target of the thesis is to develop practical uncertainty estimation methods using deep learning approaches that are scalable to object detection. Specifically, I focus on 3D object detection using LiDAR sensors and in the context of autonomous driving. This video shows the probabilistic car detection on the LiDAR top-down view from a detector developed from this thesis. Here, cars are recognized with classification scores and their bounding boxes are predicted with confidence levels. In the following, I would like to present my thesis contributions in 4 aspects. First, I will introduce the methodology to capture holistic uncertainty. That is, to model different types of uncertainty and in different network architectures. Then, I study the explainability of the modeled uncertainty and show that they reflect detection accuracy and observation noises. This is very important because we need to make sure that the modeled uncertainty encode information what they're designed for. Afterwards, I will discuss how to evaluate the quality of uncertainty with the help of calibration plots and propose several methods to reduce uncertainty estimation errors. In general, a calibration plot provides us a direct way to understand and interpret uncertainty. Finally, I will introduce several applications that leverage uncertainties to improve the detection performance, both in training and testing phases. In order to introduce the methodology, let's formally define the problems of object detection. A LiDAR-based object detector usually takes the raw LiDAR point cloud as input, denoted by X, and makes predictions denoted by Y, including object classes, Y class, and their bounding box regression parameters, YB box. The object class is represented by an integer from 1 up to C number of classes, and the bounding box is encoded by several parameters, such as the centroid location, length, width, height, and orientation. The network is characterized by its trainable parameters, or weights, denoted as W, and it is optimized with a training dataset D. In order to model uncertainty in object detection, I follow the idea from the seminal work from the Alice Kendall, who suggests 2 types of uncertainty that we can model in any computer vision problem, namely the epistemic uncertainty and the aleatoric uncertainty. The epistemic uncertainty indicates how the model fits the training dataset. It is also called the model's uncertainty. Ideally, it should be small within the training data and large outside. It will also decrease when feeding the network with more data. The aleatoric uncertainty, on the other hand, describes the observation likelihood from the model's output and indicates the observation noises inherent in sensor and environment. It cannot be explained away with more training data. As an example, in semantic segmentation shown in the figure below, very different behaviors between aleatoric and epistemic uncertainties can be observed. In general, understanding different types of uncertainty is important for safe autonomous driving, as the epistemic uncertainty displays the limitation of detection models, while the aleatoric uncertainty provides the sensor observation noises that might be useful for other modules, such as tracking and prediction. In the fetus, the epistemic and the aleatoric uncertainties are estimated following the Bayesian neural network framework. A Bayesian neural network assumes that the network weights, W, are random variables with a certain probability distribution. The predictive uncertainty, Py given x and d, can be decomposed into two types of uncertainty through modularization over the network weight. When we explicitly model Py given x and w, we estimate the observation likelihood or the noise corruption at the network outputs. This is the aleatoric uncertainty. When we estimate the posterior distribution of network weights given the training data, Pw given d, we estimate how well the model fits the training dataset, and this is the epistemic uncertainty. In the following, I will introduce how to model aleatoric and epistemic uncertainty respectively. To estimate the aleatoric uncertainty, I employ the direct modeling approach. In this approach, we need to assume a certain probability distribution in the network outputs. As an example, here I assume that each regression parameter for 3D bounding box follows a Gaussian distribution with its mean and the variance denoted by mu and sigma square. The classification follows a categorical distribution with its mean denoted by p. Then the output layers from the network are directly modified to predict the parameters of probability distributions. In our case, that will be the mean and the variance for the Gaussian and the mean for the categorical distribution. Finally, the network's weights are optimized. In other words, the network is trained through the maximum likelihood estimate, resulting in the loss function shown on the right. In the case of a regression, we obtain the attenuated regression loss, which incorporates mu and sigma square in the loss function. In the case of classification, we obtain the common cross-entropy loss. As for the epistemic uncertainty, a common strategy is called the sampling approach. In this approach, instead of inferring the posterior distribution analytically, we collect the samples, draw for some approximate distribution of Pw given d, and calculate the sample statistics. In the fetus, Monte Carlo dropout and deepening samples are employed to the object detection, which are two well-known sampling-based methodology for uncertainty estimation in deep learning. This small animation illustrates how MC dropout works. During testing time, we perform dropout inferences from the same network architecture and collect samples to calculate uncertainty, such as sample mean and sample variance. In the fetus, I introduced the epistemic and the aleatoric uncertainties in several common ladder-based object detectors. The detectors are convolution neural networks roughly categorized into the two-stage and one-stage object detectors. For more information, please refer to my fetus. Having introduced the methodology, now I would like to show the second contribution of my dissertation, which is to study the explainability of the modeled uncertainty. Again, this is important because we need to make sure that the modeled uncertainties encode information what they are designed for. First, I studied the behavior of epistemic uncertainty. This type of uncertainty is found to be affected by the detection accuracy. The following plots show the distributions of epistemic uncertainty for predictions in autonomous driving dataset. The uncertainty is measured by the total variance scores for all accurate predictions on the left and inaccurate predictions on the right. The detection accuracy is measured by the intersection of a union, or IOU scores. The higher, the better. We can observe that for accurate predictions with IOU larger than 0.8, Most total variances are small, indicating small epistemic uncertainties, whereas for inaccurate predictions on the right, the distribution of total variances is spread out with many large values. In these two videos, I used the epistemic uncertainty to threshold detections. Detections with high epistemic uncertainty are marked in red, whereas detections with low epistemic uncertainty in green. It can be observed that many false positives and bounding boxes with strange shapes are predicted with high epistemic uncertainty. This indicates that the modeled epistemic uncertainty is reasonable. It shows the model's capability when describing data. As for the aleatoric uncertainty, I found that it reflects environmental noises in the LiDAR perception. On the left video, I show the change of aleatoric uncertainty for a car marked with a green bounding box. As this object is approaching to the ego vehicle, its uncertainty score is decreasing, indicating smaller aleatoric uncertainty. This is because when the car is getting closer, there are more and more LiDAR reflections, and it is easier for the detector to localize this object. The right image shows that the aleatoric uncertainty is affected by occlusion. Here, the uncertainty scores on the backside of objects are consistently larger than the front sides facing towards the ego vehicle. This is because the occluded areas have fewer LiDAR reflections and it is difficult to estimate the positions there. In general, I found that the detection with sparse LiDAR points tend to have higher aleatoric uncertainty. This small video gives you a more detailed impression on how aleatoric uncertainty is increasing. Due to detection distances, occlusion, orientations, and many other factors, the LiDAR points within an object can be pretty sparse. Correspondingly, the uncertainty scores tends to be high. This indicates that the aleatoric uncertainty represents reasonable environmental noises in the LiDAR perception. Next, I would like to introduce the third part of my thesis contributions, which is to study the quality of uncertainty estimation with the help of calibration plots. This provides us a tool to easily understand and interpret uncertainty estimation. From the frequentist point of view, a model should predict probability that matches the natural frequency of correctness. For example, if a model makes predictions with 0.8 probability scores, intuitively, we expect 80% of those predictions should be correct. This way of evaluating uncertainty can be illustrated by a calibration plot shown on the right. Here, the horizontal axis shows the predicted probability from the model, and the vertical axis shows the empirical probability or frequency, usually calculated based on the dataset. An ideal model should predict probability that always matches the natural probability, resulting in a diagonal line. In practice, however, due to the network architecture design or training process, the network may produce underconfident or overconfident uncertainties, resulting in a blue curve that is different from the diagonal line. In the thesis, I evaluated the performance of LiDAR detectors and found out that the predictive uncertainties are miscalibrated, resulting in a blue curve on the left. Propagating this miscalibrated uncertainty to the downstream modules can be dangerous, especially in the decision-making process in autonomous driving. In this regard, I propose three novel methods to reduce uncertainty estimation errors, namely isotonic regression, temperature scaling, and calibration laws. They are quite efficient and work in constant time complexity, which is highly desirable for online deployment. Let us denote P as uncalibrated probability from the network. The basic idea is to train a small recalibration model, G, that maps uncalibrated probability P to some better calibrated probability denoted by BP hat. I verified the proposed methods in several standard autonomous driving datasets and found that uncertainty estimation errors could be largely reduced, achieving a nearly perfect calibration plot shown on the right. Uncertainties should not only be explainable and well calibrated, they should also be useful in practice. In this regard, the final contribution of my thesis is to apply uncertainty to object detection both in training and testing. In the first application, I leveraged the electrical uncertainty to improve the detection accuracy in light object detectors. The method is straightforward. I train the probabilistic detector by the maximum likelihood estimate, and the network learns to adapt the noisy training samples with the help of electrical uncertainty. The table here compares the 3D car detection performance on the KT dataset. First, I build a baseline LiDAR detector without any uncertainty estimation. It achieves on-par results with other well-known LiDAR detectors such as MC3D, Foston PointNet, and Pixar. Then, I train a model with the electrical uncertainty from the baseline network. Here, the new network consistently improved the baseline method with higher average position scores, especially in hard detections, showing the benefits of modeling uncertainty. In the dissertation, I have also conducted experiments using different network architectures and in other public datasets, including the USINGS and the Waymo datasets, and achieved consistent improvement. In the second application, I extend electrical uncertainty from LiDAR detectors into a fusion network that combines raw LiDAR point clouds and RGB camera images. The motivation for sensor fusion is to exploit the complementary properties between LiDAR and camera sensors in a data-driven manner for more accurate detection. First, I employ the previous method to model electrical uncertainty in the LiDAR branch. Then, I propose to propagate those uncertainties into the fusion network through a simple sampling mechanism. In this way, the fusion network is trained with more diverse training data and learns to handle different levels of uncertainties. The right figure illustrates that the proposed method improves the network robustness when input sensors are unsynchronized. The horizontal axis represents the increasing positional errors between LiDAR and the camera inputs, and the vertical axis represents the average position performance. At the same level of positional error, the proposed sampling method largely outperforms the models without sampling, up to nearly 20% average position. It also outperforms the network trained from the sampling with a fixed variance, showing its improved robustness against the noisy data. Finally, I apply the epistemic uncertainty to improve the training process of an object detector. In general, training a deep neural network requires a huge amount of label data, and annotating data is a very tedious and time-consuming work, especially when dealing with LiDAR. In this regard, I introduced the epistemic uncertainty to train a LiDAR detector through the active learning framework. In general, active learning is a training strategy in machine learning which aims to reduce the number of data labels while maximizing a model's performance. I verified active learning in a small object detection network, and its benefit is shown in the learning curve on the right. Here, the active learning with epistemic uncertainty estimates is compared with a standard baseline, which randomly selects training samples to label and train the network. To achieve a certain level of detection accuracy, active learning requires much fewer label samples compared to the baseline method, showing its benefit in reducing human labeling efforts. To summarize, the main contribution of the thesis is to develop practical uncertainty estimation methods for object detection using deep learning approaches. Special focus was on 3D object detection using LiDAR point clouds. I studied 4 aspects of uncertainty estimation, that is to capture holistic, explainable, well-calibrated, and useful uncertainties. I would like to highlight that my dissertation is the first work in the research community to capture different types of uncertainty and study their behaviors in object detection. It is also the first work to verify that leveraging electrical uncertainty can be used to improve detection accuracy. It is also the first work to introduce uncertainty in sensor fusion deep learning, as well as some of the first works to study uncertainty calibration and active learning in object detection. Many open research questions remain. For example, how to capture comparable uncertainty among different sensor types, how to get better uncertainty estimates for out-of-data distribution, in other words, the long-tail problems, how to propagate detection uncertainty to the downstream modules, such as tracking and prediction. Here is a list of my publications during my PhD study, including 3 IEEE transactions and a few conference and workshop papers. Some of my works received Google citations above 100, and I also had the opportunity to have an oral paper presentation in the IV conference and gave an invited workshop talk in the IROS conference. I feel very thankful for my supervisor for guiding me through my PhD journey. I would also like to thank my advisors and collaborators for the nice discussion and brainstorming during my PhD. It is an unforgettable experience, especially during this special time of global pandemic. For more information about my research, please check my personal homepage or contact me directly. Thank you for watching this video.